Is it?
Yeah, I was done actually with the bio. No, almost done. I think 3 years ago I was back to Italy with Vita Levi Montalcini fellowships and back to Padua, where he's still now, and now he's an associate professor at University of Padua. So Marco is an expert mostly in condensed matter physics, in particular ultra cold atoms, many body physics, and topology, having overlap with a number of things we are interested in here. And today he will give a talk on effects of frustration and degeneracy from vortex phases to flat bands dynamics. Please.
Thank you, Francesco, and thank you also for the invitation and you for the patience of being here to hear me. I will try to tell you a bit of the research activity that has been going on in the last years and some results that are kind of connected and maybe interesting also for you. And I would like to call the attention on flat band dynamics, which looks like an oxymoron, a contradiction. I will try to tell you why it's not. Let me start about what does it mean, flat bands, degeneracy, why these things are interesting. Okay. We are talking about degeneracies, and degeneracies, for example, are some features of single particle spectra. One of the most famous examples is the Lib lattice, which is also famous because it's the copper oxide plane of cuprate superconductors. It's a lattice with a special unit cell. You can see there is different connectivity between certain sites and others. And the effect of this is the presence of a zero energy flat band, giving rise to localization. And what does it mean? It means that there is some non-trivial interference process. For example, an eigenstate of the flat band looks like this. Here I'm highlighting the red sites. They are occupied equally, but with different phase, and they have destructive interference in the corners. So you see, this is an eigenstate of the Hamiltonian, but there is no propagation. It's a compact localized state. So why are objects or systems of this type interesting? They're interesting because interactions now are quenched, are important all of a sudden, and can induce non-trivial many-body problems. If you take two of these states and nearby plaquettes, they share one site, for example, and if I have interactions among particles on the shared site, you can jump, let's say, from this state to this other, so localization is gone, and collisions form some sort of emergent correlations that can be highly non-trivial. How much non-trivial? Your imagination. One of the most famous examples that has been identified in the last years is the twisted bilayer graphene case. You see here there is a zero energy flat band or almost flat band. So no kinetic physics, no single particle effective physics. Everything is driven by interaction. And it's so non-trivial that you have a superconductor even for repulsive interactions like the famous ITC superconductors. So correlations of a non-trivial nature. Another interesting example, I'm only citing a few of them, connected to what I'm interested in, is, for example, the one of frustration induced by an external magnetic field and the degeneracy of Landau levels. So this is a two-dimensional problem, electrons in a stronger perpendicular magnetic field. If you solve this problem, a single particle, you have a series of harmonic oscillator, but each harmonic oscillator has an additional quantum number that gives you a very large degeneracy. How large? Macroscopically large, exponentially large. And now if you take particles and you put them, let's say, in this lowest band or this lowest set of states, of course, if for every state there is a particle, you're done. This is the integer Hall. But if the occupation is lower, fractional, then the degeneracy becomes again macroscopic. How do you resolve this degeneracy? Again, take interactions. For electrons will be Coulomb, but you can imagine of different types of interactions, project them onto these states, and look what happens. And we discovered in the 80s, this is the famous Nobel Prize picture, that what happens is a many-body state that has a fractional Hall conductivity and interesting many-body excitations like anions with non-trivial fractional statistical number. Yes. So this is another example of how interactions and degeneracies can give rise to competing effects and non-trivial phenomena, emergent phenomena. Okay, my main interest is quantum simulation. So quantum simulation platforms, mostly ultra cold atoms, but not only, Rydberg atoms. So the question that I would like to address is, okay, we have these highly tunable, highly engineerable systems, and they can help us understand more the effects of correlations, of strong interactions between particles of the type I was giving you examples a moment ago. And the advance nowadays is such that you can engineer different type of models of highly tunable performance, bosonic models like Bose-Hubbard that we'll talk about, Fermi-Hubbard, or is spin models, and this you can do either with atoms or that are mobile, or atoms that are pinned, the Rydberg atom situation. And the toolbox that we have now available, at least at the analog case, I will not discuss digital quantum computers or digital settings here, is very large. Since the beginning, when it was proven the high controllability to get a quantum phase transition, now we have in the toolbox the possibility to control and understand many realms of many-body physics, from strongly correlated dynamics that it's hard to compute with numerics, to SUN models, topological phases, lattice gauge theories, and so on and so forth. Okay, in this context is what the work I will present today is going to address some relevant topics for me. So I will talk mostly about three topics on degeneracies and frustration. One is possibility of engineering or observing vortex phases, many-body vortex phases, something quite elusive so far. A second part on observing dynamics in flat bands, still single particle, no interactions. And then a possibility also to have dynamics in flat bands via interactions, and in a setting that it's probably of very much interest to you, which is waveguide 3D. Okay, let's start this little journey by asking the questions of what is fundamental in the physics of the quantum Hall or the fractional quantum Hall, and what is fundamental is the absence of time reversal. A magnetic field breaks time reversal. So if you want to see this type of physics, you have to be able to break time reversal in your system. In the electron gas is the magnetic field for a charged particle, but if you're using atoms that are neutral, what do? You have to resort to all the tricks of quantum simulation, quantum engineering, to mimic or reproduce the same effects. For example, you can engineer a synthetic magnetic field, which means a complex hopping such that a total phase, Aronoff-Bohm phase, is finite, is non-trivial. This was done, for example, for atoms already many years ago. You can even exploit the duality between the Coriolis force and the Lorentz force by putting the atoms in rotation. Or you can rotate your entire system in a circular way, shaking in a circular way, something that allowed to see the topological phases of the Haldane model. And the goal of this, in the end, besides, of course, learning how to measure and do topology, is also to enter the strongly correlated regime, some many-body physics. One is the fractional quantum Hall that we saw a moment ago, because excitations are highly non-trivial. No one directly observes anyons. So if you can engineer them and control them, it is an extremely astonishing way of studying these objects. And recently, the first Laughlin state or fractional quantum Hall state of two particles was measured, that was created in few labs, just two particles. It's a small quantum Hall state is not a phase, but it's extremely hard to prepare topological order. So this has been already a milestone in the field. But systems that break time reversal symmetry can be slightly easier, many body systems. One of them, for example, are these objects, these phases called interacting vortices and Meissner phases, in which you can think of a small quantum Hall state. You have edge state, but these edge states are basically the two sides of the ladder, up and down. And achieving this state, because it relies on the competition between hopping and interaction, was already hard, and this was done in a Floquet engineers setting only last year. So from here on, we have maybe a path toward strongly interacting fractional quantum Hall phases beyond a few particles. So the work I will present kind of concerns this type of systems. And now I ask you the following question. Do you know a way to break time reversal symmetry spontaneously without doing it externally by hand? Have you ever encountered? If you have, I'm interested. Let me know. So symmetry breaking is something we learn in school or in university as a process to have emergent many-body phases in general. Usually you talk about U1, but you can ask yourself, can this also happen with time reversal? Can I have a quantum Hall or a fractional quantum Hall without a magnetic field, without applying time reversal perturbation from the beginning? Can we? We have some examples that I will tell you about. But before that, let me give you the framework in which we will discuss this. So bosons on a lattice. So you have only hopping processes and local interactions. As we saw before, you have the possibility of observing two possible phases. If the free particle part wins, bosons will condense and form a boson-Einstein condensate. If the interaction wins, you will have a Mott insulator, a featureless Mott insulator. So one is related to the fact that you have mobility and you can delocalize and form phase coherence. And the other is the fact that if you have one particle per site and very large interactions, double occupation is forbidden. When this is the case, the system is pinned atoms and insulated. Typical phase diagram you have probably seen sometimes is this one. J over U, large J is the superfluid phase, small j is the Mott insulator, and here you have, if you want, occupation, filling 1, 2, 3. Okay, let's say we take bosons on a lattice. How do we break spontaneously time reversal? This problem was figured out a long time ago, in 2006, more or less, by asking the questions, what is the physics of bosons, not on the lowest orbital of the lattice, but on the first excited, for example, p-band. You have to bear with me with the possibility that atoms are not here, will not decay. It's not true experimentally. They decay. This is the problem. But if you for a moment forget this, and you ask yourself, what can atoms do? You immediately realize that the model you have in mind is already different than the Bose-Hubbard we saw before. Why? In 2D, you have two orbitals, px and py. So you have two ways of delocalizing. A px that moves like this, or a py that moves either like this or like that. So kinetic part is already different. But the most interesting part is the interaction part. So interactions are local. Atoms interact only when they are on the same well, on the same site. But now, besides the density-density term, there is also an additional term that couples the two orbitals px and py. And now I would like to call the attention on the minus sign in front, because this tells you that interaction, sorry, I have to tell you one thing first. So the term coupling px and py is the angular momentum operator. And the fact that it comes L squared with a minus in front tells you that if you want to minimize the interaction energy, because of the minus sign, you have to maximize the angular momentum. So the ground state of these atoms is a state in which particles rotate. Why that? Because if they rotate, in the middle there is a hole, and the middle is where the overlap is stronger. Remember, interactions are on-site. So particles want to avoid each other to minimize the energy. How do they avoid each other? Putting themselves in a vortex and in the middle nothing or little. So the ground state will be a vortex in each well. So this was done. Was also observed experimentally. And the problem is atoms can decay. So besides seeing a condensate of vortices, that's it. It's been hard to go beyond. So we ask ourselves, how can we go beyond? And we came up with an idea of engineering orbitals.
Beyond in what sense?
From weakly interacting to strongly interacting. So weakly interacting was seen in this vortex phase, but a Mott insulator or a strongly interacting, very hard because collisions make you decay. This was even measured. So let's try another strategy. We want to stay in the lowest band. So what can we do? So we started studying this frustrated lattice configuration. So it's a square plaquette with a minus sign in the opening here. If you remember the Aronoff-Bohm, it means that there is a phase of pi when you go around the plaquette. It's a twist in the boundary conditions. Usual dispersion relation is a cosine. Now here we have 4 sites, so 1, 2, 3, 4 momenta. But because of the pi, or pi fourth per each link, actually the dispersion is shifted. This shows you that the momenta create degenerate states in the single particle sector. Let's call them D1 and D2, and also call the attention on the fact that you have a gap. So how are these modes? They are delocalized all around the plaquette. These are the two representations that we used, but you can change bases if you want. And now you can play the game of projecting interaction, like we talked about in the fractional quantum Hall, in the flat band. Let's project interactions, which is local, onto these two states, which are non-local, assuming that the gap is not important. What do you see when you project interactions? That in the basis of the lowest two states, you have a density term of the usual form, but also a coupling between D1 and D2. And the coupling is also the one sort of coupling that would like to create a vortex. So if I think of an entire plaquette as my single site, and I couple many plaquettes, it's like we are engineering px and py orbitals by using at least 4 sites.
So you have S-type orbitals.
You have S-type of orbitals. But they are delocalized in the plaquette, and they have this non-trivial collision terms and interactions now. Yes. No, because it's a pi flux. Minus pi and plus pi is the same, so time reversal is a complex conjugation. So at the single particle level, there is no broken time reversal symmetry. I mean, you can go clockwise or counterclockwise, the physics is the same. Or you can think of this about the same the other way. If you have a plaquette, you can flip it, and it's still a plaquette with pi. So these are, if you think of it as a magnet, there are these two, vorticity left or vorticity right, are degenerate. So first we looked at weakly interacting case, Bose-Hubbard physics on only 4 sites, assume a condensate. You put some impurity that localize the density somewhere here, then you quench, you remove this potential, and you see what happens to this density excess. And what you find is that you can, in this way, you can see the vorticity by monitoring the motion of this density. The reason why we do it, because it's in cold atoms, you have a single atom microscope on a single site, so you can measure the density, so you can measure the motion of this impurity. This will be a probing way. Okay, some benchmark with exact diagonalization, that everything works well, and so on. Okay, so this was still the weakly interacting regime. Now we want to look at of a single plaquette. Now we want to look at many plaquettes. This is a model you may have seen. It's a higher order topological insulator, the one that has the corner modes as topological edge states. And how is it done? This model has a pi flux plaquette coupled to all the neighbor pi flux plaquette by a J prime that is weak. So I can think of using the following strategy. If J prime is very small compared to the gap I was showing you before over the single plaquette, then I can stay at low energy and still do this orbital physics. What you get, the ground state, is an array of vortices. So you have a vortex in each plaquette. And this impurity that I was showing you before appears as an excited mode with some angular momentum that can now, because of the coupling between the plaquettes, can in principle decay onto the usual density modulation of a Bose-Einstein condensate. Okay, so this allows us to go from single plaquette to many plaquettes. What about strongly interacting? What about increasing the value of Hubbard U, having some density which is 1 or 1/2? In p-bands, we know there is a transition from a superfluid of vortices to a Mott insulator of vortices. So question is, can we have the same here? So a vortex Mott insulator, for example, is something that people were trying to predict long time ago. And here actually it comes naturally. We did the MRG calculations at filling 1/2. So 2 particles per plaquette of 4 sites. And what we see is that the ground state gap, the gap between the ground state and the first excited state at small interactions is 0, the superfluid phase of vortices I told you a moment ago. But then at some point, it opens up. And this is also signaled by the susceptibility that starts diverging. Okay, then the question is, what is the phase here which has a finite gap? Is it a trivial phase or not? And what we did was to compute the current on each plaquette. And the DMRG predicts, calculation is that when you cross the transition, actually this loop current that is non-zero in the superfluid here remains non-zero across. So this is a disorder parameter, if you want, of time reversal symmetry breaking remains always non-zero. It's if you want, this is a check that you are entering a vortex Mott insulating phase. Of course, this depends on the filling. Is this true all the time? Because I was showing you a moment ago in the experiment of Eidesburger on this Meissner phase, you can in principle control the number of particles. You can prepare different many-body ground states. So we studied now this 2-dimensional setting or model by using a variational ansatz that we checked also with the MRG. And we find that depending on the filling, you have different possibilities. Half filling is the one we saw. You have a Mott insulator of vortices. At quarter filling also. Three-quarter filling convergence is being hard. We are trying to figure out what happens here because this variational ansatz, it's a cluster Gutzwiller ansatz. It's a product state of plaquette states. Does not allow you to predict what happens inside the lobes, but only outside in the superfluid phase. And then at filling one, we find an interesting difference, not a vortex MOT, but a trivial MOT. If you want, it's a MOT in which you have one particle in each site, absolutely no vortices or time reversal properties of sort. Okay, this is interesting because now you have two universality classes for the transitions. This one, in which you go from time reversal broken to time reversal broken, and this one where you time reversal now switches. Here is a vortex superfluid, so it's broken, and here is not. So what happens at critical points? At critical points, things that can appear are Higgs modes, Higgs excitation, something that you can describe by field theory. Remember what it is. If you have an ordered parameter, your ordered parameter can be excited if you have a Mexican hat, either in a gapless or zero energy way, going around. This is the phase excitation. Or you can oscillate radially, and this is the amplitude. And actually, this picture is exactly what happens when you are at the critical point here. If you compute the spectrum, you have the Goldstone, and then you have an excitation with a mass with a finite gap, which is a Higgs, the usual relativistic dispersion relation that emerges at the criticality. Yes?
Why we are Goldstone mode if we are talking about condensing?
Because if every time, no, continuous, U1, condensation, you're condensing. You are condensing. No, here you go from a MOT to superfluid. So here you're just only breaking U1. It's a circle U1, right? So the universality class is O2, the rotation group. We will go there in the next slide. So this is what usually happens in the Bose-Hubbard model. And this was measured. The gap that closes at the critical point was measured by Emmanuel Bloch more than 10 years ago. And this was the signature of a observation of a Higgs mode. But now the story I'm trying to tell you is slightly different. Why? Because U1 is only broken in this vortex MOT insulator to vortex superfluid. Whereas here, besides U1, you have also time reversal that is broken unbroken. So with these ansatz I showed a moment ago, we managed to compute the excitation spectrum and see if you can see some differences. If you're here, you have your Goldstone and your Higgs excitation. But if you are, okay, the quantity we are plotting is called flatness. So it tells you if the excitation is more radial or tangential, so amplitude or phase, Higgs or Goldstone. It's an observable we can compute from the eigenvectors. Then we can do the same here. First, we find a very different spectrum. There is always a Goldstone mode. There is a Higgs mode. You see it's red. The flatness is 1, so it's radial. There is also a second Higgs excitation. What do they differ from each other? Here is not plotted, but these are not conventional Higgs. These are Higgs with additional angular momentum. So it's a chiral Higgs. And they have different quantities or values of chirality. Why do you need a Higgs with angular momentum? Because it's the one that will carry away the angular momentum of the ground state when you cross the phase transition. So we were expecting to find, and it's there. But the surprise was the additional second Higgs. There is also some other modes that are neither phase nor amplitude, and we're still wondering what they are. Okay, So this concludes the part on how degeneracy is resolved in terms of vortices. And then I ask you another question. If you have a flat band, and I move to the second part of the talk, if I have a flat band and I have a wave packet on a flat band, its mass is going to be a ton, really heavy. I expect no motion. Can I see a motion of wave packet on a flat band? Can I see dynamics, mobility? And we try to figure out this, if this can lead to novel effects. The simplest effect you can look for is the block oscillation case. If you have a lattice, and if you add an external tilt or electric field, then you have this tilting of the potential. And I can prepare, let's say, a wave packet in this lattice under the effect of this force. You know from the equations of motion that momentum will change, will increase with the force, due to the force. And now on lattices, there is something very special. Because you see, if the wave packet is prepared here, where the group velocity is positive, then the wave packet will start moving forward. But then at some point, K, the momentum, will cross the top of the band. So we'll go to this region of the band dispersion, where the group velocity now is negative. So the wave packet first moves forward, then backwards, and this starts repeating itself periodically. And this is the phenomenon of block oscillation already demonstrated many years ago. Why block oscillations are important? They're important in the field of topological insulator and topological states because they can be used to probe the topology of the bands. The point is that if you have a topologically non-trivial band, the equation of motion I showed a moment ago are not enough, are partially true. There is a missing term, which is this anomalous Hall velocity. So is the term that is responsible for the Hall effect. The object I'm representing here is the Berry curvature that depends on the block states of the band. And now the famous TKNN formula tells you that the Hall conductivity is exactly related to the integral of the Berry curvature. So I can think of taking a wave packet that satisfies the semi-classical equations and use it to reconstruct the Berry curvature. I check the motion of the wave packet, and from that I infer the distribution of Berry curvature. So this is what people have been doing. The most famous example was the one of the Haldane model, at least I'm talking about cold atoms, where the phase diagram of the model with chair number 1 and -1, the two topological phases, were reconstructed by using the dynamics of wave packets. You see, I apply a force to a wave packet, then this is deflected to the right or to the left, depending on the Berry curvature sign. And this is the experiment, yes, cold atoms experiment. Then you have probably seen it with arrays of waveguides, Rexman, and many others. To create the Haldane phase, yes, they do circular shaking. Okay, so if you do the circular shaking, the Dirac cone of the honeycomb lattice is opened, there is a gap, and then you enter this phase, two different phases. Okay, so far, so good. The point is that what if you are in a flat band? In a flat band, the dispersion is 0. You can say, okay, I can still have a Berry curvature. But what if you are in 1D? In 1D, there is no Berry curvature. Or what if you are in 2D, but then you have PT symmetry, parity and time reversal together? Berry curvature is 0. So R dot equals 0. No dynamics. Can we go further? Now I will try to show that there is an option for going further, and we call the attention on a couple of effects, and we build a theory for it. The questions I showed or we discussed a moment ago only comes about if you have an external potential that is linear. The force, this is a constant electric field. What if I start adding quadratic or cubic? So this was done already. This analysis were started in a few works. We also extend this. So how do the semi-classical equations extend in the presence of nonlinear potential? I will show you that you get geometric contribution. I will show you that we also obtain a formulation in the non-abelian case and test it to see what you can actually see. This is the equation we obtained together also with some other people and also extend it to non-abelian. So let's drop the linear part. So the first correction is the quadratic potential. You see you have two indices. These two indices is the quadratic potential. So the velocity is now coupled via the quadratic potential to what? To the derivative of the quantum metric that usually people call it quantum metric dipole. For people who don't know or don't remember what is the quantum metric, is a quantity that characterizes the distance between block states. This is the fidelity between block states at different k, close k points. So 1 minus is the infidelity. And this is actually in differential geometry can be put formally in this structure, where G mu nu describe the metric of this space of block states.
This is a standard derivative, right? This is standard gradient.
This is the covariant derivative.
So they contain.
I'm hiding because I don't want to talk about the non-abelian part, but here this will be just a derivative plus the Berry connection. If you go from abelian to non-abelian, like in SU gauge theories, the derivative becomes a covariant derivative. I can write it if you want to. What I have in mind just to fix it. Sorry? Someone talked? No. Ah. I don't have a chalk. I don't see chalk. Okay, no problem. So it's a covariant derivative in the sense that contains the shift of the Berry connection.
Make sure I understood properly. You get this term with a quadratic potential. Quadratic is,
in space.
In space.
Yes.
Meaning a non-uniform.
Non-uniform, exactly, inhomogeneous. My electric field external that I apply, if you want, or tilt is not a tilt, but it's a parabola. So we will do that. Also in 1D. The example I will give you is in 1D. And also
the standard equation of motion for R and K, which we showed in the previous slide. So these equations rely on having a linear.
Yes, it's here. K dot equal F. And you see K dot means that here there is F now. Now, here the velocity, it does not have, it has the force, but the quadratic part. I'm not showing the momentum part because first I want to tell you about this, because the momentum actually is slightly less interesting. So if you want K dot equal F is not so much interesting, right? Because the momentum changes due to the force. Here, the velocity part is interesting because you see the velocity now depends on the metric, on the changes in the metric of your block.
Terms you get for all the terms.
These are all the terms. I'm only neglecting one term, which is called shape dependent and is lagrangeable. Capital omega is the usual Berry curvature. Here, non-abelian eventually. That's why it's bold. And this is part of our extension. So you see, there is a coupling, non-abelian coupling between the Berry curvature and the metric. If they are present together and the potential is cubic, then you have an effect. In this equation is about the non-abelian extension, yes. In this equation is also about the non-abelian extension. So if you want, the previous equations were the same, but abelian. But we also looked at the wave packet variance. So my wave packet has some size. Does it change in time? And how does it change in time? So Sousa and Pruneda many years ago found out that also the wave packet change in time with the linear potential case, and again, the metric dipole. What we find is that for the non-abelian case, there is a new term that was not identified before, and we want to test it because we didn't test it here in this work, but it's there. It's a commutator between the metric. So what do you get from these two equations? First, a wave packet in time oscillates, block oscillations, but also the width in time can oscillate, and how much depends on the metric again. Notice linear and quadratic. So you will see a moment in the numerics that this affects the numbers. The point is that what we wanted to do also here was to check if these equations were true. So some of these equations were around, but nobody had tested it on wave packets. So it was not clear if this would work. So we constructed a model to check this. The simplest model, yes. At the moment we do general. Now the next we go to 1D, where there is no Berry curvature. There is a flat band. We prepare a wave packet, and these are the equations of motion. Look, velocity along x depends on the derivative of the metric, and the width of the wave packet depends also on the derivative of the metric. What you see is that
those equations were normal. Nobody had checked
on a wave packet, I mean, how much is the displacement? Is it observable, not observable? Is there a correction that you in the calculations are missing because the computation is not easy? And so I think the variance was seen in tested by Sousa, but that's it, not in this model. So what we see is that indeed there is a block oscillation in the flat band that is driven by the metric dipole. It's small, 10 minus 3, but it's there. And then it's dumped because you start getting other contribution, non-adiabatic ones, breaks down. And also the block oscillation of the variance, but this time with the linear potential. You see, you have an initial width, let's say reference, increases and then comes back. Whoa, whoa, wobbles. A linear potential is enough. You can see that the signal is strong.
Measure the minimum spread of the variance function, right? So can one understand this as I'm introducing an external computation in this case, and I'm changing my quantum landscape and so on and modifying that bound?
No, remember it's a bound between two. It's like a Heisenberg uncertainty principle. So you can change the variance in real space, but you have to modify also the variance in momentum space. And this is where the wobble goes. So you can oscillate in the momentum space, in the real space variance, at the cost of satisfying this uncertainty. If you want, the uncertainty tells you that your Vanier functions have a certain spread. So yes, they are connected in this way by that. Okay. So this was the 1D. We also did a 2D version where you can see a sort of Hall displacement. I don't do it. But now you say, how do you do a Hall? Well, there is a metric dipole, there is a metric, and the metric has XY components. So that is enough to displace transversally your wave packet, even though you have no Berry curvature. So careful when you see transverse displacement, it may be coming from a metric in the system and not the Berry curvature. I will not show because to keep everything things short. Now what we're doing is to construct a system where we can see non-abelian effects. This was the first preparatory work to understand if the equations were good, were working, and how things were happening there.
Stupid question. I mean, this equation for W is general, right? Even in standard band.
Yes.
So why did you consider a Batman to use this?
Because at first we were.
This maximizes the effect. Or?
I think a dispersive band would work anyway. I should think about it maybe a little bit more.
Just understand the rationale.
No, the rationale was to. No, the rationale was to try to see dynamics in flat bands and of wave packets, and to understand whether the equations of motion would have some contribution of inhomogeneous potential. So once we were there, we just generalized the equations of motion.
But this behavior W in that equation, you can see this also in a standard band, in a dispersive band.
I would say so. Yes. I have to think about it again, but I would say so. It's true, but also for the width, the only contribution you have, where is it? So the leading contribution. So there is not. So here I'm dropping the linear part, right? I'm only showing you the quadratic. Of course, there is also the linear part, but for the width, there is nothing. I mean, the leading contribution is this. Yes. Yes, the leading is this one. So you should see the effect there anyway. No, not here. I mean, there is there is a term H0. Okay, this answers the questions. There is an additional term that contains the single particle Hamiltonian that here, since it's flat, does not give you geometrical effects like some weird Berry phase on top. So for maybe I think I'm wrong. There should be another contribution here that goes to zero in the flat band case. Oh, in general, this contribution is there.
Yeah, the term that is missing here is bigger than that one, so that's why maybe you don't see this effect.
We didn't check the numerics in the dispersive band, so I cannot answer this question. It's interesting. It's a check we should have done, actually. Yes. Yeah. So yes, one of the important issues here is non-adiabatic effects. So you want to remain in the band you are considering. So the gap to the other bands is relevant. True. Exactly. So there is, but this is a nonlinear. These are nonlinear effects. It's not a nonlinear potential. That's the difference. And also there, you start coupling to the metric. So here, if you want, we're doing linear response of an inhomogeneous potential. What you're discussing is nonlinear response of whatever potential. Yes? Yes.
Now, if there is non-constant non-homogeneous potential, what is the shape of the spectrum? What is kind of an because you are superimposing a band which is that they are filled that induces a dispersion.
I agree. So So the answer is that is I think is not analytically integrable. The structure of the ladder. I don't think we computed the spectrum at all directly. We worked directly in the equations of motion case, but this is interesting question. I would say locally is linear. Then you can do a sort of local density approximation, and you could see a sort of spacing, and this linear spacing increases over the energy space. Yeah, the question.
No.
Oh. Okay, so this was dynamics via nonlinearities, and I will close. I don't know how far I am. Oh, I'm very far. On dynamics via interactions, which is something we started discussing in the context of waveguide QED. So this is probably a Hamiltonian or a model that you know very well, a one-dimensional waveguide, atomic array, photons can emit bidirectionally in the waveguide, and this generates long-term couplings, which are periodic and do not decay in principle. Now, excitation can jump from any atomic array to any other mediated by the photons that go through. And this is the polaritoric dispersion in 1D. Okay, but flat bands are an interference process. So it means that if I perturb my model, I start introducing long-range coupling, goodbye flat bands, most probably. What about a setting like this where you have arbitrarily long interactions? So we constructed a Lie lattice of atoms coupled to one-dimensional waveguides. And one-dimensional, we wanted one-dimensional because there is this perfect periodicity of the couplings. Very nice to control things. And instead of using the usual two-level atoms, we consider a nonlinear resonator, just to assume, give the possibility of interactions. So like you can have a ground state, you can have an excited state, but if you have two photons, you have a nonlinearity, a shift. And now what we find is that instead of losing completely the flatness of the band, if you choose the spacing D commensurate with the lattice, with the the wavelength of light, you can fine tune the interference processes that preserve chiral symmetry. What does it mean? For example, a red atom, of course, along this waveguide can jump anywhere, but I can fine tune such that the purple rate of hopping is exactly 0. And if I do that, the lattice becomes or remains bipartite. Red is connected to red, purple is connected to purple, and blue is connected to blue. This allows to keep a completely flat, perfectly flat band, and also gives you an additional gap, which you don't have in the Lie lattice. So the gap of the Lie lattice has no special protection symmetries like Haldane model. You can open the gap if you put some couplings. And this is good because this gap allows to isolate energetically the middle band. This band is also non-trivial. It has a finite quantum metric. Why all of this is interesting? It's interesting because we wanted to study if there is bound states, two photon bound states, and if they are dispersive. So you have localization at the single particle, single excitation sector, but in the interacting case, if you remember first slide, collisions can couple different sectors and objects can delocalize. So we compute the two excitation sector near the flat band, and we find that there are dispersive bands. So these are bound states. This is the relative coordinate that goes quickly to 0 with respect to the center of mass. And so this is first you have bound states. They are dispersive, which means they are mobile. They can delocalize in this Lib lattice of waveguides. And the only energy scale that sets the existence of the bound state from our dynamics is interactions. I will not say more. Now, this connects to the fact that the quantum metric is actually responsible for the mass of bound states. This was proven in this work by Torma. If you have a Cooper pair or generally a bound state, a low energy, this can be explained, the size of the mass, by the quantum metric. However, this result was obtained only for a single bound state, isolated band. But here we have two of them. So the finding that I think is interesting is that this result of this Lib lattice in waveguide QD requires to be done a non-abelian formulation, multiband, that extends or identify why there is such a structure in terms of the quantum metric, assuming that it's the only ingredient. Maybe there is more ingredients there. So I conclude. I talked about how pi flux can help you break time reversal symmetry with interaction and producing vortex phases and Higgs excitations. I told you that localized, flat bands can still provide transport properties, assuming you have nonlinear potentials or you consider the width, the spread of the wave packet, and also that flat bands can be protected even with long-range interactions and give rise to novel types of bound states in 2D. Let me acknowledge who was involved: Maria, Gincin, Lorenzo, Mattia, Giuseppe, that you may know, then Nathan Giandomenico, and other collaborators. Thank you.
One thing that often comes up in the geometric physics stuff is that some of the results must be reversed to reparameterization of the variable. Is that the case here? Is what happens? And what's the meaning of your reparameterization?
Reparameterization depends on what?
Your parameters here are better if the momentum, right?
Yes, you always have to be careful with the wave packet coordinates if you're thinking about the wave packet part.
Yeah, the middle.
Yes. So for the wave packet, when you implement the equations, for example, you have to be careful. If there are